All right, so Assalamu alaikum everyone. Today we're going to start our sixth lecture, and this lecture deals with directions and planes. Thank you. Inside crystals. So we've reached a watershed moment in our course. We've completed one module already. That module dealt with the crystalline state and describing the crystalline state. What are crystals? What are the symmetry properties of crystals when viewed from the outside world? And what goes inside the crystal? There are atoms and electron densities. What are the symmetry properties of the arrangement of atoms inside a crystal? And then we were able to bunch up all the possible arrangements of crystalline matter into 230 space groups. Now, reading these PS groups is a complicated but a quite a pleasant and delightful experience in its own right. I uploaded some international tables on our website, and if you go through those handouts, you'll be flabbergasted and amazed by the richness and the variety of the atomic arrangements. So we've just scratched the landscape of the concept of space groups. So now, however, we do have a good handle on describing the crystalline state.
सर
Yes.
बच्चे ग्रुप में कह रहे हैं कि आप कल आपके किसी नई लिंक पे उन्होंने ज्वाइन किया वो चल नहीं रहा
Acha, एक minute. So just wanna. So I sent two links in the morning. Is this the old link?
आई प्रिज्यूम इट्स द ओल्ड वन सर
So I sent two links. One is for the office hours and one is for the course. So
आई एम गोना सेंड दिस लिंक टू देम इन द ग्रुप नाउ कि वो इसको ज्वाइन कर लें
okay. So I hope you haven't just. What link have you? There are two links. One is the link for the course, and the other is the link for the office hours. So these are not the office hours. These are rather the course web link. So can you please ask your colleagues
यस
to
सर
join?
आई एम सेंडिंग देम दिस लिंक
Okay. All right. So let's continue. So we've discussed how we are able to describe the crystalline state. Now we're going to switch gears a little bit and we're going to move to the second module of this course. And this second module deals with, excuse me, this second module deals with how do we get to know about the crystalline state in the first place. For example, no one can peep into the solid and tear apart the surface of the solid and go inside and see what's going on inside the solid material. Rather, one has to use various kinds of probes. And three probes are often used for probing crystals. One of them are neutrons. Then, in some cases, we have electrons. And the third probe are X rays. So now we have these three kinds of probes. And X rays include the new area of synchrotron radiation, which are X rays of a special kind, highly energetic and highly intense beams coming out from a cyclotron. Electrons could be used in an electron microscopy experiment, and neutrons could be used in a neutron diffraction experiment. So these three probes are the most popular probes of probing into the crystalline state. Now, in this second module of the course, we're going to deal with two concepts, and two concepts in tandem together. One is the concept of diffraction, particularly diffraction from X-rays, because that by far remains the most important and the most versatile tool for probing the crystalline state. But in the process, we'll also describe a beautiful and highly mathematical concept, and that is of the reciprocal space. And in order to understand the reciprocal space, we need to know a little bit of Fourier theory. So that's what we're going to do in the next today and in the next 2 or 3 lectures. So before I move on and start this module, I would like to invite any questions. Homework number 2 has been uploaded, by the way. The solution to homework 1 has also been posted. Any questions?
सर
जी,
ये सिंक्रोट्रॉन इसमें क्या होता है सर, थोड़ा इसमें डिटेल बता दें।
synchrotron. In a synchrotron, you have a ring, a large ring in which electrons are accelerated to very high energies. And since these electrons are charged particles, when they accelerate, they give off radiation in the form of X rays. Now, this is extremely intense beams of X rays. These are collimated, and then they could be used uh, for, for diffraction or other kind of studies. So, this is the working principle of a synchrotron. Okay, and you set up a station here and perform a particular experiment. This is called a beamline. So there is a synchrotron in India and there's one in Jordan, which is called the Sesame, in which Pakistan supposedly should be involved in a particular beamline. All right. So any more questions, my friends, before we proceed?
सर
जी,
सर हमने रेसिप्रोकल लेटस पढ़ा था, ये रेसिप्रोकल स्पेस और लेटस में क्या फर्क होता है?
कोई नहीं, अभी आ जाएगा आहिस्ता आहिस्ता पता चल जाएगा.
सही
So in real space you have direct lattices. In the reciprocal space you have reciprocal lattices.
सही सर।
All right, so before I move on, I'd just like to finish off on one small topic which I inadvertently missed from the previous lectures, and that is by looking at a space group, can we tell what the point group of the crystal is? So, as you know, the point group determines the rotational symmetry of the crystal. You hold a crystal in your hand, you look at it from the outside, what kind of symmetry operations uh, does it harbor? Uh, this would include rotations and mirror reflections. That tells us the point group of that crystal. So by looking at the space group, can we tell what the point group of the crystal is? Of course, we can do that. The difference between space groups and point groups is that space groups include translations. We're ignoring the lattice translations. They are trivial. That's how we define a crystal. But in a screw axis or a glide plane, there are translations associated with rotations and reflections. So if we suppress those translations and ignore those translational symmetry elements, we'll arrive at the point group of the space group. For example, for diamond, we have the space group F 3 bar M. This is the space group of diamond. Now, if you would like to find out the point group for this crystal structure, so if you pick up a crystal of diamond in your hand, really expensive, and something that has fascinated the imagination of mankind, men and women alike, for ages. You pick up that crystal in your hand, a diamond crystal. What would be its point group? You do rotations, you do reflections, you'll find out the point group of the crystal, but that can be derived from the space group. So finding the point group of that crystal from the space group is also easy. So you just ignore the first centering indicator, the FPIC, you ignore it. You replace all glide planes by mirror operation. So this diamond D glide plane is replaced by M. A roto reflection remains a roto reflection, 3 bar, and an M remains an M. So the point group of this space group is M 3 bar M. Likewise, if I have a hexagonal space group P 6 3 MC. Now 6 3 is a screw axis. You replace 6 3 by 6, a 6-fold rotation, M remains an M. This glide plane, the C glide plane becomes another M. So this becomes a 6 M M point group. Likewise, if you had the monoclinic P2 sub 1 forward slash B. Now 2 sub 1 is a screw axis. You replace it simply by 2. This symbol remains, the perpendicular symbol goes as it is, and the B glide plane becomes a mirror plane. So you get the monoclinic point group 2 forward slash M, and so on. So by looking at the space group, you can tell what the point group of a crystal is. All right. So now let's start our today's lecture formally. First of all, I would like to talk about directions in a crystal. So any questions up till this point from the previous lectures or from the homeworks? I've also announced the office hours, uh, 3 to 4 p.m. But in case that someone is not available, I can also extend them, or I can meet outside these times as well. So we don't have many students today, it seems, or we do. Okay.
सर वो जो आपने नई लिंक भेजी है वो चल नहीं रही है, पुरानी लिंक पे ही स्टूडेंट्स ने लॉग इन किया है।
तो नया लिंक नहीं चल रहा?
नहीं।
All right. So I'll check that. But can someone send a link to Umema? Today I sent 2 links. One was the condensed matter physics class, and one was for the office hours. Is this the old link that you're currently using?
Yes, sir.
Okay. So far, so good then. All right. So let's talk about directions in a crystal. But let's first of all talk about, it's easier to talk about, it's more difficult, but let's start with the difficult thing, planes in a crystal. Now suppose I'm talking about 2 dimensions only. I have a plane lattice. Okay, so let's draw a plane lattice. And it's a kind of a square plane lattice. Now this could also be the projection of a cubic 3-dimensional lattice, or uh, a tetragonal 3-dimensional lattice. But in 2 dimensions, it's square. All right. I define my axes. I have an x-axis and I have a y-axis. Sometimes I would call this x-axis the a-axis and the y-axis the b-axis, in keeping with standard crystallographic nomenclature. So now, so far I haven't put atoms on this lattice. These are just crystal, these are just lattices. I can, of course, put on atoms and equip or clothe this lattice as well. So it will eventually become a crystal structure. Now, what I would like to do is let's draw planes inside this lattice. And atoms will, of course, be on the planes. Now, what I would like to do now, I would like to do place atoms on this lattice, and I will put an atom on each of the lattice points. So my basis is just a single atom perched on the lattice points. So I had the lattice and now I'm putting atoms on top of it. And there's 1 point per unit cell. So this is really a primitive lattice. Now, if you look at this crystal structure, which has now been composed of a lattice and bases, these atoms can be viewed as being lying in planes. So I could talk about this plane. This is a plane of atoms, a surface of atoms. Here is another plane, and another plane. So I have a family of planes. All right, so far so good. Now I would like to identify this family of planes, and I would like to label these planes. I would, in other words, like to index the planes. I would like to identify the planes. And why are these planes important? Because planes play an important role in diffraction studies. That's just one application of the concept of planes. So if the planes that I've drawn, how would I identify these planes? So what I would do, this is my, sorry, this is my unit cell length A along the X direction, and this is my unit cell length along the B direction. So what I do is I start from any point. Let me change the color again. I start from any lattice point here and move along AA, along the X direction. And I would like to see how many crossings of planes do I get while I make a hop from one lattice point to the next lattice point. So let me rephrase this. I start at a position, say A, and I move in the X direction. At some point, I will have advanced by a unit translational vector and would land on the neighboring lattice point, which is B. And I would like to count the number of crossings of planes I make in this journey. I just make one crossing, and that is at B itself. So I write the number 1. Then I do a similar hop from point A to point C along the y-axis and count the number of crossings of planes that I encounter. I just see one crossing, and that is at C itself. Right? Or, sorry, if I move from A to B, if I move from A to B, do I see any crossings? I don't see any crossing at all because the crossing is at the point B. So I write down the number 0. Similarly, if I were to move from A to C, I do not make any crossing whatsoever. So I write the number 0 again. Now, if I were to move along the Z direction, then would I okay, just hold on, please. Just hold on, please. Just give me a second. I'm just slightly confused here. Okay. Let me backtrack a little bit. I was मैं ठीक ही कह रहा था. So I'm at point A. I'm at point A and I move in the X direction. Ultimately, I will reach point B. So how many crossings of planes do I make? I see one crossing which is at the point B itself.
सर
जी जी.
सर जिस तरह ये हमारे पास दो प्लेन्स हैं, इनके दरमियान वैसे अगर देखा जाए तो क्रॉसिंग तो है नहीं, मतलब ए पॉइंट से बी तक इसमें कोई क्रॉसिंग नहीं है। अगर हम मतलब ए से नीचे अगर आते हैं मतलब थर्ड प्लेन पे, तो फिर क्रॉसिंग आती है उसमें एक। इस तरह
तो
कैसे, मतलब आइडिया दे
इसको
दीजिए।
क्रॉसिंग कह लें, इसको स्पेसिंग कह लें. क्रॉसिंग तो है. If I start from A and I move towards B, I do see a crossing at B. All right. So there is one crossing in advancing from A to B. However, when I move from A to C along the y direction, I do not see any crossing because I'm moving along the plane. So I put a number 0 in the second position. Okay. So suppose this were a three-dimensional lattice and I moved at starting from point A along the z direction. I'm still moving on a plane because these are vertical planes. So I do not see any crossing as I move along the z direction. So I put a number 0. So this trio of numbers 1, 0 and 0 in the proper order.
सर इसमें
Excuse
हम
me,
ये
let me
कैसे,
finish. Let me finish yaar, khatam karne do. So if I have this trio of numbers 1, 0 and 0 and I put them in parentheses, this will become the Miller indices of these planes. All right. Ab pucho.
मैं ये पूछना चाहता था कि मतलब ए से बी के दरमियान चांसेस हैं कि और भी प्लेन हो सकता है, इसलिए उसमें क्रॉसिंग आ गई है।
चांसेस हैं, अगर और प्लेन हुए तो प्लेन होंगे या नहीं होंगे. अब ए की क्रॉसिंग आ रही है फ्रॉम ए टू बी एंड दैट इज एट पॉइंट बी. यू इंटरसेक्ट at point B, you intersect or come across or encounter a plane. And that is why there is one spacing or one interplanar spacing as you move from A to B. Okay. So that is why I put the number 1. G Heather.
सर ये मिलर इंडिसेस एब्सोल्यूट तो ना हुई, ये तो एक प्लेन की किसी दूसरे प्लेन से रिलेटिव हुई ना, कि 100 अगर आप ए से बी में जा रहे हैं तो फिर ही होगा, अदरवाइज अगर किसी
अगर
और
आप you take any lattice point, you take this lattice point uh, and you move from this lattice point C to D, and then you move from C to E and from C to F, you'll get the same indices. Yes, please. There are
सर
other
लेट्स से
participants.
अगर हम बी से ई में जाते
क्या क्या?
हैं, सर लेट्स से अगर हम बी से ई में जाते हैं तो उसका लेटेस्ट
You
मिरर
you
इंडिसेस
need
क्या
to move.
होंगे?
You need to move. You can't go from B to E. You need to move across one unit cell.
सही सर, अब समझ आ गई सर, थैंक यू।
All right. So let me draw some more planes. So these are lattice points that I'm drawing. Not atoms as yet. So I define my axis, my x-axis and my y-axis. Now let me draw some more planes. So I have a plane here, vertical plane. I have a plane here. I have a plane here. So these are my planes that I would like to index. Okay, atoms can lie on these planes. So far, I haven't put in atoms. Now, what I would like to do is I move from one lattice point to another. Along the x direction, I make two crossings. Then I move along the y direction, I make none crossing because I'm moving along the plane. Then I move along the z direction. starting from my original point, I do not make any crossing. So the Miller indices of the planes that I've drawn are 2, 0, 0. Got it? Likewise, I can go on. I can draw more Miller indices and more Miller planes. Right? So let me try to do something more tricky here. And so on. All right. So now I would like to identify the Miller indices of these planes. So I move along the x-axis, I get one crossing. I move along the y-axis, I also get one crossing, and none along the z-axis. So the Miller indices of these planes are 1, 0, 0. All right. So let me draw another scenario. Once again, a square lattice. And let me take the liberty of drawing more mirror planes. Oh, sorry, more planes. So these should be straight lines really. If I drew my grid properly, these are straight lines. Now I could do exactly the same thing. I move along X, I get two crossings. I move along Y, I get one crossing. So these are the mirror planes 2, 1, 0. These are the atomic planes 2, 1, 0. All right, so now let me do something else. Draw a big lattice, square lattice, just to do many things at once. And still, this is a two-dimensional projection of three-dimensional lattice, and I'm drawing vertical atomic planes. Okay, so we've already noticed that this is the family of planes identified by 1, 1, 0. Okay, now let's do the following. Mm, now I have these planes. All right, so what would be the Miller indices of these planes? Of course, the two kinds of planes that I've drawn, they appear different, so they must have different Miller indices. Now, in order to look at this problem, let's consider the following. If I'm standing at this location, say A, and I move along the x-axis, so my x-axis is always downward, and this is my y-axis. So I move from A to B. What I'm trying to do is I'm going from up to down. And when I move from A to C, I'm also going from up to down. Now, if you look at the two curly arrows that I've drawn, they are piercing this atomic plane from the same side. Both of these arrows are piercing the plane from the same side. So consider this blue line, this plane to be a piece of cloth. And the crossings that you make, consider them to be like needles and you pricking the cloth. So when I'm advancing in the X direction, I'm pricking the cloth from one particular side. And when I'm advancing along the Y direction, I'm pricking the cloth from the same side. So here is my needle. I'm pricking the needle from one side, and here I'm pricking the needle into the cloth from the same side of the fabric. So that is why I have a 1 and a 1. Now, if I were to do the same process on the planes that I've drawn on the right, so what I could do, I could start off at this point A, move downwards by 1 unit. There is one crossing 1, but then I move in the Y direction. There is also one crossing. So now if you look at the two arrows that I've drawn, and let me draw the needles now. So if I'm going in the X direction, I'm pricking this piece of cloth in this direction. Okay. And when I'm going along the Y direction, I am piercing my cloth from the other side, from the rear side of the plane. So I would put a -1 on top of the second index that I've written. And the minus sign is symbolized by a bar on top of the number. So I have 1, 1 bar 0. 1, 1 bar 0 would identify the crystal planes that I've drawn on the right side of this figure. Okay, do you get this point? I could also have written 1 bar 1 0. It wouldn't make any difference whatsoever. Both of these Miller plane indices are the same. They are counted as the same. Okay, so now I could draw more mirror planes. Heather, just a
Direction.
minute. Just a minute, please. So let's, so the indices for these Miller planes would be, so I go from here to here, two crossings, go from here to here, one crossing, 2, 1, 0, and so on. Yes, Heather.
Sir, I'm confused about the points where these planes intersect. Will
These
there
planes
be,
do not intersect.
sir, what about these two lines that you've drawn, uh, ऊपर, so the third lines हैं. So if
ये
you
वाली
extend these
जो
lines,
राइट पे, राइट पे,
राइट में भी और लेफ्ट में भी दोनों जो थर्ड वाली हैं, once you extend these, shouldn't these intersect at some point?
no, no, these are parallel planes. These are all parallel planes of atoms. They don't intersect.
I'm sorry, I didn't understand where we got the one bar from. क्योंकि the direction is the same. जब हमने left side पे किया वही चीज़ हमने right side पे नहीं की.
नहीं, बिल्कुल ऐसी बात नहीं है. So you have planes on the left and you have planes on the right. They have different orientations. They have to be identified by different indices. So if you look at the left, if I move from A to point B, look at the directions in which I'm piercing the planes. So I'm piercing the plane from this side, which I've drawn in red. Okay. And when I
Yeah.
move from A to C, I'm also piercing the same plane from starting from the red direction. So my needle is going into the piece of cloth, which I'm symbolizing as the plane from the same side. Therefore, the two numbers 1 and 1 have the same sign. Both of them are positive. I could also write 1 bar 0. It doesn't matter. Both of these indices represent the family of planes that I've drawn on the left. On the right hand case, this is not the case. If I go from A to B, which means I advance along the x direction, I am piercing the plane from this side. Okay. However, if I were to move along the y direction, then look at the kind of crossings that I'm making on the plane. These needles are piercing the plane from the other side. So
Yes, sir,
in
now
one
I
case, I'm going
understand.
from up to down, and in the other case, I'm going from down to up. So that is why the mirror planes on the right, one of the numbers will have a minus sign on top of them. Okay, so let me try to describe this in 3 dimensions. Let me draw a 3 dimensional cubic lattice. Other most other authors of crystallography use a different mechanism for labeling the Miller planes, and I'll also talk about that approach a little bit. So this is a cubic lattice. Okay, so this is my x-axis, this is my y-axis or the b-axis, and this is my c-axis. Now let me draw a plane. The first plane I would like to draw is very simple. This, of course, is a plane. This plane is the same as this plane because of the periodicity of the lattice. Okay, so these two planes are equivalent. They are just two faces, oppositely lying faces of a unit cell. Now, if I would like to index this plane, I move along x. I move along x. I do not make a plane crossing, so I get a 0. I move along y. I do not get a plane crossing. I get a 0. However, if I move along z, I do get one plane crossing throughout the length of the unit cell. So I get a 1. So this is the 0, 0, 1 plane. Likewise, this will be, what would be the Miller indices of these planes? 0, 1,
0
0.
1 0.
Exactly. And now let me draw another plane. So I connect two diametrically opposite edges. So I get a slanting plane. Could you identify what the Miller indices of these planes would be? So when I move
101.
1, 0, 1. So in the entire crystal, I will have many
101.
1, 0, 1. Yes. So in the entire crystal, I will have many planes of this kind, a family of planes.
सर जी 1 0 -1 क्यों नहीं है?
Because when I move along the, let me see. Sorry. So it's let's see. If I move along the x direction like this, I am piercing this plane from the bottom. Okay, from the back side. And when I'm moving along the z direction, I am also piercing this plane from the bottom, from the same side. Therefore, it is 1, 0, 1. Got it? So I will have a family of planes, 1, 0, 1. All of them will be lying inside the crystal. And there will be an infinite number of them because my crystal is infinite. It's assumed to be infinite because the surfaces are minuscule as compared to the number of atoms inside the crystal. The atoms that reside on the surface, they are just tiny. So I will have a family of 1, 0, 1 planes. And atoms, I could have atoms organized on these planes, or I could not have any atoms, but at least the planes are now identifiable. If I would like to,
Sir,
can you, in this cube, let me just finish, my friends. If I have this crystal, this cubic cell, and I would like to identify planes 1, 0, 1 bar, what would those planes look like? Can you give it a shot?
डायमेट्रिकली ही होगा, लेकिन आई गेस इस जो हमारा है पहले आपने बनाया उससे ऑपोजिट में होगा, फ्रंट टॉप फ्रंट फेस और बैक बॉटम.
Exactly. So this plane is the 1, 0, 1 bar plane. All right, I can draw as many planes as I like. So let's draw some more interesting planes. So I'm just sticking to the cubic for the time being. If I were to draw a plane of this kind, what kind of plane is this? What are the Miller indices?
सर 1 1 1.
These are the 1, 1, 1 planes. Okay, so let me now bring up a few examples which I've interestingly kept for you. So someone had a question.
सर वो मेरे पिछली स्लाइड से था, अगर काइंडली आप एक पेज पीछे आ सकते हैं.
एक मिनट. Just need to. कहाँ पे?
सर इससे पिछला पेज 210 जो आपने लिखा है, 201 था.
Right. This one, right? 210.
यहाँ पर माइनस क्यों नहीं आया सर एक के साथ, क्योंकि हम एक को ऊपर से pierce कर रहे हैं और प्लेन को नीचे से pierce
Sorry,
कर रहे
sorry. 2 1 bar 0.
हैं. अच्छा, alright, ठीक है, ठीक है.
सर हमारा ये
Now
जो
let.
प्लेन है 101 बार और 1 बार 01, ये इक्विवेलेंट होंगे?
नहीं, बिल्कुल नहीं.
तो सर फिर हमारे जो पीछे हमने जिसमें हम दोनों को नीचे से पियर्स कर रहे थे, हमने दोनों के ऊपर बार क्यों नहीं कर दिया? उस तरह से नहीं हो सकता था?
कौन से में? किधर आप बात कर रहे हो?
सर ऊपर जो ब्लू प्लेन बनाया था आपने, ये जो 3 जहाँ पे प्लेन्स बने हुए हैं इस फिगर में, जो
ये
पहला
the
ब्लू
blue
प्लेन है।
red.
हाँ जी, इस वाले में जहाँ ब्लू रेड ग्रीन है, इसमें जो ब्लू प्लेन
Yes.
है, इसमें अगर हम एक्स से मूव कर रहे हैं उसको भी हम नीचे से पियर्स कर रहे हैं, और जी से मूव कर रहे हैं तब भी हम नीचे से पियर्स कर रहे हैं।
So that's why we have 101. We can also write 1 bar 0 1 bar. It doesn't matter.
ऑल राइट। और सर काइंड ये बता दें कि अगर 1 बार 01 होगा तो वो किस तरह की ओरिएंटेशन में होगा?
1 bar
01, ये 101 बार बना हुआ है ना यहाँ पे, अगर 1 बार 01 होता?
1 bar 0 1 होता है. यानी you would like to have 1 bar 0 1.
यस सर।
It's the same as this thing. They are the same. You could put a bar on either.
ठीक है, सही, यही कंफर्म कर रहा था मैं पहले। ठीक है।
Now let's look at these mirror planes. Okay, let me try to see if I can make this bigger. All right. So now the definition in these diagrams has slightly changed. So this is my a-axis. My a-axis, this is my b-axis, and here is my c-axis. Okay. So now if I move along A, I get one crossing, so I get a 1. I move along B, I get two crossings, I get a 2. And I move along C, I get three crossings. So these planes that have been drawn, they're these wedge-shaped planes, they are indexed as 1, 2, 3. Likewise, this is 3 along A, 1 along B, and 2 along C. So these are the 3, 1, 2 planes. So these planes are really, if I would like take the liberty of drawing these planes look like this, wedge shaped. Okay, here is one of these planes. Here is another plane belonging to the same family, and here is yet another one. Okay, so these planes are indexed as 312. Here I have 103.
Sir,
B.
could you draw it on a cube जिसकी back वाली faces भी हमें नजर आ रहे हैं, because this is like a little difficult to visualize.
Let me try. Drawing these are difficult, so let me try drawing 312. Okay, let me try. So I call this my a-axis, I call this my b-axis, and I call this my c-axis, right? I had the liberty to choose my axis, okay? So this is my b-axis. I would like to draw planes 3, 1, 2. So I need three crossings on A. So I put one just placeholder here and a placeholder here. So I have three gaps or three spacings along A. I have one spacing along the y-axis. So I draw a point here. And I have two along Z. So I draw. Right. So now what I would like to do, I connect this point to this point, and I connect this point to this point. Okay. So here is one of the planes. Okay. I'm only showing the plane inside my unit cell of interest. Of course, this plane extends to the entire three dimension of the crystal. Okay.
Yes, sir.
Now, next plane, let me just also draw the next plane. So I connect this to this, connect it here. So this is the next plane of the 312 kind. Okay. And if I were to draw yet another plane, that plane would extend to the neighboring unit cell. And here it will also go to the neighboring unit cell. So somewhere up here. So this is how I will build all the planes of a particular Miller index family. Okay. So do you get the point now? Now another a more common approach which is used by most authors in crystallography is the following. Somehow my OneNote is just stuck. So bear with me for a minute, please. All right. So if I look at this, suppose I look at the 312. Look, I look here. So one approach is the following, which is commonly used in most crystallography textbooks, and authors use this. So my one node is slightly behaving sleepishly at the moment. Just get stuck for some odd reason. So just want to restart my one node. Okay, any questions in the meantime? Okay, here you go. So if you look at, let's focus here.
सर आपकी
सर
स्क्रीन शेयर
स्क्रीन
नहीं
शेयर
हो
नहीं
रही.
हो रही.
मैं कर रहा हूं, कर रहा हूं. So I hope I'm recording. All right, so if I move along X, this is my X direction now, my A direction or my X direction. The plane that I'm interested in intercepts the X axis at the location 1 by 3. Okay, and it intercepts the Y axis at the location 1/2. And it intercepts the Z axis at some location. So B, sorry, this is my B axis. This is my B axis. So it intercepts the B axis at a location 1, and it intercepts the Z axis at a location 1/2. So I get 1 by 3, 1 and 1/2. What I would like to do next is I would like to invert these numbers. So I get 3, 1, 2, and these become my Miller indices. So one can look at the Miller indices by looking at the intercepts of those planes along the A, B, and C axes and then inverting them. If a plane is parallel to the axis, it never intercepts. So you start off with an infinity and you invert it, you get a 0. So this is the approach that is commonly used in most crystallography textbooks. So I'm talking about more of a graphical and an intuitive approach of indexing these Miller planes. Now in the cubic system, if you notice, it's not a nice cube, but nevertheless. So my one node is slightly behaving really strange. It's not allowing me to draw anything at the moment. Sorry about that. I am sorry, it's just, let me stop sharing for a minute and let me also pause recording for a minute, resume recording. So in interest of time, let me see if I can restart the, all right, so my video is back. Let me see what's the status. So let me share my screen again. I'm sorry, guys. This is beyond technology is beyond control sometimes. All right. So I've talked about Miller indices. Now I need to talk a little bit about directions. Now directions is the easy stuff. Okay. So if I draw a lattice, and this is just a two-dimensional projection of a lattice. Let me take the liberty of now drawing a monoclinic lattice. So here is my x-axis and here is my y-axis. Now what I would like to do, I'm interested now in finding out directions inside the crystal or inside the lattice instead of planes. I've talked about planes, so far so good. Let's talk about directions now. So consider this direction here. So I can represent directions, of course, by vectors. So this is a particular direction. This is another direction. This is yet another direction. Another direction. Yet another direction. So I can draw directions inside the crystal. And now I would like to identify these directions by suitable indices. Now let's do this indexing one by one. If I look at this arrow here, how in order to specify this direction, what do I need to do? If I move along the x-axis by 0 units and by along the y-axis by 1 unit, I've actually followed the direction that I've earmarked. So this direction is 0 along x, 1 unit along y, and 0 units along z. So the direction index is 0, 1, 0, and I put it in square brackets. Now let's look at the second arrow here. In order to specify this direction, I have to move 1 unit along x and 1 unit along y. So the direction is 1, 1, 0. And now let's look at this direction. I can always extend the directions to any length whatsoever because a direction is just a direction. So when I start from point A and I reach another lattice point B, how can I reach that lattice point? I can reach that lattice point by taking 2 hops in the x direction followed by 1 hop in the b direction. So this direction is 2, 1, 0. All right, and so on. So this direction will eventually meet some lattice point because it's an infinite dimensional crystal. And when it meets, I can count the number of hops that I've made along x and the number of hops that I've made along y. Okay, and then I can specify that direction. The arrow that I've drawn over here is simply 0 units along x and 1 minus units along y and 0 units along z. So this is how I can identify directions, and these directions are specified by labels u, v, and w, and they're always written in square brackets. I was talking about a cubic unit cell before the connection was severed. So let me draw this unit cell here, cubic. And what I wanted to specify is that if this is a purely a cubic unit cell, then this plane will be equivalent to this plane and to this plane because it's a cubic unit cell. All the x, y, and z directions are equivalent, and this will also be the same as somehow my OneNote is just not keeping up with me. I'm sorry about that. My OneNote is just stuck. All right. So it's also going to be equivalent to the plane that I've drawn here. So all the six faces of this cube are equivalent. Therefore, the planes, that's why you wouldn't like to have online classes all the time. So the planes which are 1, 0, 0 is a face of the a cube. 0, 1, 0 is another face. 0, 0, 1 is another face. All right. So these three planes uh, are all going to be the same in a cube. All right. So I can represent these planes by another symbol which is given as 1, 0, 0. So if I put the 1, 0, 0 in these carets, the left caret and the right caret, it really specifies all three of these planes, and all three of them are equivalent in a cubic cell. Now there are some more slight corollaries that I would like you to be aware of, and one of them is, I think I'll have to let go with this because my OneNote is just behaving. Let me try to shut down a few things. Let me try removing one of the images that I've inserted. Let me try. Mm, let's see if it makes a difference. All right, now I can draw planes. So I can, let me draw a plane, a particular plane. Can you immediately, if this is my x-axis, this is my y-axis and z-axis, can you immediately tell the Miller indices of this plane? 2, 1, 2, correct? Now, if I were to choose a particular direction, some direction, U, V, W, and I have a plane HKL, I would like to ask whether the direction lies inside that plane or not. Okay, so whether direction U, V, W lies in a plane or not. So in order to answer this question, and I'm going to state this without a proof, I can tell whether it lies in the plane or not if HU plus KV plus WL is 0.
Dot product है ये.
This is the dot product, but these are not really vectors, so I'm not calling it a dot product. Okay, because HKL is not really a vector, it's just a Miller set of Miller indices. So if this condition is satisfied, then the direction UVW lies inside the plane. So for this particular this particular plane, if can you identify a direction that would lie inside this plane?
1 2 minus 2
1 2,
minus 2.
so 2 times 1, so exactly, so this direction 1 2 minus 2 will lie inside this plane, and I can make an attempt of drawing this direction, and you could do this as a homework perhaps. So I move 1 unit along x, I move 2 units along 2, so this is, so right, and then I move 2 units, okay, and I move 2 units in the downward direction. So I get, so this is my, this is this particular direction. Okay, there are other directions that also lie inside this plane. This is not unique. There's an infinite number of directions that lie inside this plane. So what I've drawn in orange is really this direction here, 1 2 2 bar. It's coming downwards, sloping downwards, and in a particular orientation. All right. So I can all G Heather.
सर ये जो डायरेक्शन के आप कोऑर्डिनेट्स लिख रहे हैं ये इनका इंटीजर होना तो जरूरी नहीं है ना, ये कोई भी नंबर हो सकता
So if it's not an integer, if it's a fraction, so suppose it is like 1 by 2, 1 by 3, 1. So what you would like to do is you would like to make this these integers. Okay, so this would become 3 to 1. So you multiply by 3 to 6, sorry, which, so this is the direction 3 to 6. So you normalize and make this, you rationalize and make this into integers. Okay. Now the second point I would like to highlight is that if I have two planes, H1, K1, L1 and H2, K2, L2. So I draw two planes. So this is one plane, H1, K1, L1, and then I draw another plane. Okay, so these are two planes, H2, K2, L2. Of course, they may intersect somewhere. They may intersect somewhere. And if I would like to find the direction of at which they intersect, so one of these directions could be this, the other direction could be the exact diametrically opposite. So I could do that by forming a matrix. So my unknown direction is U, V, W. So suppose one of the planes is 1, 1, 0, the other plane is 1, 2, 1. So I put the unknown direction U, V, W, then one of the Miller indices 1, 1, 0 in the second row, the other in third row. I make this matrix, and then from here I could find out the indices in the following fashion. U equals 1 minus 0, which is multiply these terms with these terms, I get 1. V minus V equals 1 minus 0, which I multiply this with this and this with this, I get 1, which means V is minus 1, and W is 2 minus 1, which means that I multiply these two numbers and these two numbers and subtract. So 1 minus 1, 1 is this particular direction here. 1, and this direction would be 1 bar, 1, 1, 1 bar. Okay, so I can find out the direction at which two planes meet. Likewise, I can, if I have two directions, I can also find out what plane does those direction lie does those two directions lie in? So if I have two directions, u1 v1 w1 and u2 v2 w2, two directions, right? Of course these directions are going to lie in a plane. Some plane will harbor both of these directions. You can always form a plane that captures or has both of these directions in it. And the unknown indices are h, k, l. So I form a similar matrix. And through a similar procedure, as I've done before, I can find out the Miller indices h, k, l. Sometimes I also have multiple planes. And those planes can all intersect with one another. So if I have planes of this kind that intersect, then these planes are said to belong to a zone. This is a zone of planes. And the point of intersection of all of these planes forms a line which is called a zone axis. Just to give you an example, I'm so sorry, the OneNote is just really sluggish at the moment. It might be due to the fact that I'm zooming in too much.
सर आपके पास प्रोबेबली एसएसडी नहीं है, इसलिए शायद ये मसले आ रहे हैं आपके सारे।
क्या क्या नहीं है?
सॉलिड स्टेट ड्राइव, एसएसडी एक नई तरह की ड्राइव होती है, वो आजकल ये ज़रूरी ही है अब विंडोज़ वगैरह यूज़ करने के लिए।
I'm
बड़े
actually
समय
using
लगा।
a Surface Pro.
इसके अंदर भी आई गेस ऑप्शन होगी।
मेरे ख्याल में it already has a solid state drive.
हम्म।
Anyway, so let me give you an example here. Let me at least try if the technology keeps up. Before the next lecture, I'm trying to fix this somehow. Don't worry about it. I'm sorry, it's not responding. I might need to do this in the next class. So anyway, I'd like to stop here. Sorry, there have been these technological speed breakers. But what I've tried to do is I've tried to come up with a mechanism of identifying and indexing Miller indices and planes, and I've come up with some mechanism of identifying directions. I can find out the plane in which two directions lie. I can find out if whether two planes intersect. How do I find out the direction at the point of intersection? I I can find out the zone axes, etc. So probably inshallah we'll meet on Thursday. I'll try to fix this technology glitch before that. I don't know how I'll do that, but I'll just try to see if I can find another software. But I'll be happy to take any questions at the moment.
सर आपने जो लास्ट वो हमें प्रोवाइड किया था, एक बुक ही आपने प्रोवाइड की थी स्कैन करके, तो इट वाज़ वेरी हेल्पफुल। अगर उसी तरह से हमारे स्पेस ग्रुप से आगे जो हमारी डिस्कशन हो रही है उसके लिए भी कोई रीडिंग मटेरियल मिल जाए तो दैट वुड बी ग्रेट।
I'll probably scan the subsequent chapters of the same book.
Go
but
ahead, sir.
most of this literature is really not available at one location, and the kind of formalism that I'm using, the kind of intuitive pictures that I'm trying to build, they are not very, they're not commonly available at one place. Okay, so let me try for one last time. I'm getting slightly impatient. Let me try one last time of showing you something. No, I'm sorry, it's not keeping up. All right, so thank you very much. uh, I've announced my office hours. I'll be available on those office hours. I'll also send you my phone number, my WhatsApp number, in case you would like to ping me. And if I'm not available during those office hours, you can always ask me to immediately connect onto Zoom. I've shared the Zoom link for the office hours that is going to be distinct from the Zoom link for the class. And thank you very much. And Khuda Hafiz.